Good afternoon. So today I'm going to give an overview of an extension that's been added to the EPECentre calculator, and it's very timely as it got released, I think, earlier this week. So the EPECentre calculator is a tool that's been developed in collaboration with the University of Canterbury, parts of the EPECentre and the electrical computer engineering, and hosted and supported by EECA, which has been a great hosting organisation for this. I'd like to acknowledge there's been a number of people that have worked on this. I think it began as a third pro project and has continued on from there. So just to give you a brief outline, I'll start with overviewing the EPECentre calculator for those that aren't familiar, and then I'll talk about how load shifting was implemented and show you some impacts of the load shifting and just talk about where we could possibly go with the EPECentre calculator in the future. So the EPECentre calculator really consists of three main parts. Starts off the important part, the generation, and for this you put in an address specific location. The tool goes off and talks to NIWA Solar View, which provides the climate data for the nearest station. It also takes into account some topology of any surrounding hills. So there's some irradiance data in there and temperature. Then there's some energy calculations which take into account the array size of the PV system you're looking at to calculate in kilowatt hours, taking into account different standard assumptions around losses and a temperature derating. The next part is what does the load of the household look like, and for this we've utilised about 18,000 half-hourly load profiles from different households, and these were analysed and categorised into different user types. And the final piece of the puzzle was looking at the financial analysis. Now we've done a net present value calculation, and this is because we've considered it as an investment asset. And that's because if you are putting in a solar system and you're connected to the grid, it's not really a separate use like you might get a new car. It's actually an investment because if you don't have this, you've still got electricity. So what's the financial benefit and what's the payback time look like? And if you want further details, there's a paper on our website. Just take a look at that. So next I'll look at how load shifting was implemented. But firstly, what is load shifting? Well, this is a householder choosing to use load at a time when you're expecting to have more generation to increase your self-consumption, and that's because you get a lot better value. So what we mean by self-consumption is the amount of solar you use from what you generate. So it's really about minimising that export to the grid. And so why do you want to do that? Well, when you look at the import prices and your export prices, it's pretty obvious that any solar generation that you can use yourself comes at 4 times the benefit, as export prices are in the order about 4 times less. So when EECA talked to us about implementing this, they said they didn't want just a knob that you can dial up and say, oh, look at this, I've got 100% self-consumption, I've got 50%. They wanted to be able to link it to some physical behaviours to be able to help us with the whole point of the tool is also about educating the public. So which loads do you want to load shift? Well, electric hot water is a really good load to look at. We've got this big thermal storage. And you really can shift when you want to heat that without having too much impact on your daily life. So this is a really great one to shift. Loads, there's always a lot more dissension about which loads are good, but the loads we were asked to look at were the dishwasher and clothes washers and dryers. So those were the sort of more flexible loads that we were asked to look at. So the how to do this, the tricky question is we weren't dealing with an individual's own load profile. So really we didn't know what the loads were in that exactly. They've been aggregated and medianised to bring typical loads. So the real question is, well, where do you shift it from and where do you shift it to? So we looked at 2 different ways of load shifting. The first one is the fixed load shifting, so using things like timers or perhaps delay functions on your appliances. Hot water, you can have smart cylinders where you can fix the time, or you can get an electrician to put in a timer to shift when you want to shift your load. And you can do the similar for flexible loads if they have delay capabilities or so-called smart appliances. But really what I'm calling smart load shifting is when we look at things like home energy management systems or hot water diverters. And I'm really going to focus on hot water diverters here. So for those of you who aren't aware of what hot water diverter does, it's smart because it has a sensor that it looks at what's happening and when you're exporting out to the grid. And so when it says, okay, I'm exporting, this is a great time to turn on a load so I can reduce that export. So as well as looking for excess generation, it also is able to modulate the output. So it's not suitable for all loads, but things like hot water, a simple resistive load, it'll actually modulate it using burst, fire, or pulse width modulation to reduce the load down to whatever you're exporting. Oh, the last point is, very timely after FinSmarts, this doesn't work particularly well with controlled circuits, so you don't really want to have your distributor trying to control your hot water as well as your hot water diverter. You can get into all sorts of trouble and end up with not a suitable solution. So the shifting load from, given that we've been used this aggregated data and not individual homes, we looked to remove the hot water load evenly across the profile. So when we looked at data from EECA, and typically your hot water load's around about 27%. So what we've done is taken the load, taken 27%, which you know these peaks are quite likely a lot due to hot water, and remove that and to reintroduce with your shifted load later. And this was similarly done for appliances. The tool provides options about how often you want to use your appliances. Do you do your washing every week or every day or every second day? And so for the days that we choose to shift, it takes it evenly off the load. So where do you shift to? Well, if you've got a timer, that's really obvious. You can get the tool to calculate your maximum generation over the year, which is the best time, depending on what the tilt is perhaps of your solar panel. The hot water load is centered around this maximum generation time. And for appliances, you can stagger it around those maximum generation times. So when we were modelling the diverter, this took a little bit of time to understand. There's a lot of hot water diverters on the market and they don't all operate the same way. We also looked at a lot of different models for how we would address the hot water diverter. I'm trying to do a very simple look at thermoclines and what's happening as you use the load. In the end, we settled on using what we call the energy state model. So we assume that there's a maximum energy state of the hot water, and we've used some parameters which closely align with a New Zealand manufactured hot water diverter by Paladin. So you have a maximum temperature, which is, this is 73 degrees, and you have a minimum temperature of 40 degrees. And that hot water model, some diverters monitor your hot water temperature, some don't. So this particular model, we're looking to see if we're taking too much hot water out and you're dropping your temperature too low of your hot water cylinder. So this keeps track of your hot water state. When you had a load event for your hot water, it drops the temperature. When you've got a chance to heat it, it heats it up. So you export when T is above T max, when T is less than your T maximum of your hot water cylinder. And when it's less than T min, you're going to heat it regardless of whether there's export, just so that you keep some hot water in your cylinder. So because we're slightly increasing the temperature of the hot water cylinder, this also assumes that you have some sort of tempering valve, so you don't risk burning your householders. So as with all good models, there's a number of assumptions, and I've just put the main assumptions on this list here. We've already talked about the hot water load being assumed to be 27%. We've assumed a hot water element size from what we could gather the most common is about 3 kilowatts. This is more important in the timer analysis. It's less important in that hot water diverter because it's often modulating this load anyway. There's a typical cylinder size of 180 litres for the hot water diverter, and the minimum and maximum temperatures that I described earlier. Now, some hot water diverters, when they monitor the export, some of them are able to just whip in there very quickly and switch that load depending on their sampling rate. The Paladin claims to have pretty close to 0 watt. Some other hot water diverters we looked at, they won't start kicking in a new load until it gets up to about 200 watts. So yeah, the devil is in the detail. For this case, we've assumed a 0 watt best case. So for the different loads, we've used EECA sales and efficiency data to get a typical load for a typical instance of washing or drying clothes. So now I'd like to look at some of the impact you can see from looking at the load shifting. This shows summer day generation load components for, say, a typical scenario of a 3 kilowatt array. The user is about a sort of mid-electricity user, 7,500 kilowatt hours per annum. And if you look at the generation in red, I've got the blue curve represents this hot water assuming a timer. So this hot water has been off. So when you turn it on, it's going to be heating on full tilt. So you can see in this case, it's overwhelming the array capacity for that time. If you look at the diverter on the right-hand side, you can see that the hot water diverter model, as soon as it starts to see export, which is about this time, it turns on the hot water diverter. It switches on the hot water cylinder, start heating, and you can see it's matching very closely the generation. And so it gets to this point, it's heated its hot water cylinder, it turns off and continues on. So you can see the difference between the sort of smart hot water diverter and just a fixed timer. And that's more pronounced, particularly when you're looking at cloudy days. Also, if you've got different loads, it's smart enough to see if you've got some other load operating. So this is some results over a number of different scenarios for the same sort of 3 kilowatt array, same electricity consumption. And if you look at these are boxed whisker plots. I've got 3 different scenarios: your base case without the load shifting, timer, and hot water diverter. And you can see if the red lines represent the median result, and the boxes are 25th and 75th percentile of results. So you can see we're starting base case of an order of sort of 50% here. We're implementing a time, we get improved self-consumption, about, I don't know, 6 or 7%, and the hot water diverter improves to about 20%. So in terms of how does that translate into first year savings, you can see that for the base case in the order of about $725, the timer has improved it to about $775, and the hot water diverter is up close to around $870 savings in this first year. And this was assuming electricity rates of about 28 cents on the import and about 8 cents on the export from memory. So just to look at some possible future work for the EECA solar calculator. In the short term, we've just got some access to be able to do some further validation. We had in the past done validation of the solar tool, but we've been able to get some more recent panels and data to do this. So that's on the agenda. It's also very interesting to consider that the implications of the electricity pricing review that was done over the last year, and the government's response came out last month. And what we've seen here is some indication that pricing is going to change, particularly this will have an impact on solar. Things like the low user fixed rate looks like it might go out the window. This could have the implication of fixed cases increasing and perhaps per volume decreasing. So this is going to be an important thing to take into account when we're doing these financial analyses over 25 years, because we really don't know exactly what's going to happen there. Now, in the longer term, I've just put some ideas that have been kicked around. These are definitely not formalised or agreed, but obviously it would be very interesting to add some battery storage to this. And I think householders would be very interested to be able to do the numbers, because battery storage, it's becoming more common, and I think people would like to be able to have some indication of whether it's a good idea for their situation. We've had a lot of discussion about changing loads, particularly EV charging. And the advent of heat pumps has also increased the amount of summertime air conditioning use. So loads will be changing that need to be included. But I think if we're going to be considering EV charging, we're really at the state where we need to have householders input load. I think ideally that was always desirable to be able to get consumers to be able to load in their own smart data. However, this is not so easy, and the trade-off between simplicity was decided, but hopefully that will change in the future. There's also some interesting advances in PV technologies. Bifacial solar panels are starting to ramp up now, so you get generation for the top side and the bottom side. There's also some smart solar modules that are coming out, which instead of being limited by a single cell in your module, it can take into account if there's some shading going on with one or some defect in one, and you can get each cell working at a more optimal amount. So that will have some improvements in the solar side of things. But that's where I'd like to finish there. I did have a link, which has disappeared, to show you, but I'm sure you can find the EcoSolar calculator if you want to find it. And I'd like to thank our sponsors, supporters.